So continuing into the second, I probably was just pointing at a bunch of stuff that you couldn't see off the screen. So the second question is, what is the velocity of the rock when it hits the ground down here? So what is the velocity of the rock when it hits the ground? You first might wonder if you have to figure out when does rock hit the ground. And the truth is that's pretty easy. So the ground, see y equals to 0, down is positive, so the ground is at location y equals to positive 75 meters. So when does rock hit the ground is answering the question of y of what very special, so double star, what very special time is it such that y is positive 75 meters. And this is just going to be another quadratic formula, but instead of 0, it's going to be 75 meters. So the way that translates is that 75, you're going to subtract it from both sides. You have 0 again, so it'll be negative 125 sitting there. So that's the only place that's going to change, is instead of negative 50, this will be negative 125. So inside the square root, that minus and minus is even bigger positive number, so it's an even later time. You could follow that through. So then you find t double star, and then you ask, what is v of t double star? So once you have the time from this problem, you stick the time in there, and then you can directly answer, what is the velocity of the rock when it hits the ground? Another way to solve this problem, though, so I'll let you finish this. You can start here, and then you could even use some of the stuff I was like pointing my finger at forcefully. But yeah, you can finish this, so you finish. Okay, but you can also use this. This is pretty neat. There's a formula or a relationship shown in your book that's only appropriate for free fall or for constant acceleration problems, of which free fall is an example. So since this is a constant acceleration problem, you can use this. The velocity squared at some later time, I'll call just time 2, is equal to the velocity squared at some initial time, I'll just call number 1, plus 2 times the acceleration times the displacement. So since we're talking about y direction, I'm going to put in the displacement is y, like this. So this is the displacement that would have happened between the time number 1, the earlier time, and the time number 2, the later time. And between those times was this constant acceleration, and between those times was this particular value of displacement. So displacement is not distance. You have to be really careful, but this is a displacement. So the displacement, delta y, for our problem, this is where it starts, and this is where it finishes for us. This is time number 1, and this is time number 2. And I want to know what is the velocity at time number 2. And that's after displacing through the distance of 50 plus 75. It's not including the up-down part. It's just purely where was it at the beginning, where is it afterwards. And you'll notice that since down is positive, this is a positive displacement from 1 to 2 because down is positive. So the positive displacement is 50 plus 75. That's 125 with a plus sign, 125 meters. The acceleration is 9.8 meters per second squared, and since down is positive, you put a plus sign. So I've got the 2, the 9.8, the 125, the initial velocity squared. So the initial velocity is 20 meters per second upwards. Up is negative, so the initial velocity is a negative velocity, but when you square it, the minus sign just disappears. So you're going to put negative 20 meters per second, and then you're going to square it, so that minus sign goes away. So it's a positive and a positive, and the velocity at the ground is just the square root of this business. And it does have a plus or minus. Of course, you're going to take the plus because it is headed downwards, and down is positive. So you can get the velocity at the ground squared equals, or take the square root, take this positive square root, 20 meters per second squared plus 2 times 9.8 meters per second squared times 125 meters. And that'll be the velocity.